Again, my name is Brian Schoenholz. I'm from the Glenn Research Center, antenna researcher. So we'll talk about the CLAS-ACT activity. CLAS-ACT stands for Conformal Lightweight Antennas for Aeronautical Communications Technology. It's a bit of a mouthful, but we only need to focus on three of those words. We're looking for conformal, lightweight antennas. We were a 2016 CAS start, so we've been around a little bit. So I have the task to take you from concept to flight test here in 14 minutes. So hold tight, I'll try to cruise through a bunch of slides. So we'll get right into it. Unmanned aerial systems is a growing community. It seems like we're constantly getting new platforms. They're constantly becoming lighter, faster, longer endurance. The performance on these aircrafts are just going through the roof. But one thing remains constant with all of them. We need secure and reliable communications. We have a pilot on the ground, we have a drone in the air. If we lose that C2 link, we have a very unsafe situation, as everybody's talking about in the other presentations. So we want to avoid that. One of the means that we use is what we call line-of-sight communications. So if the pilot can see the aircraft and we can send a radio wave from a ground station to the drone, we have a reliable link. Unfortunately, or fortunately, we have a lot of aircrafts that can go well outside of that line of sight coverage. If I draw your attention to the map here on the right, I'm not sure how to use this laser pointer, but the map on the right, if we have a drone operator at NASA Wallops on the top of the East Coast, a line of sight vehicle will be restricted to that magenta radius around the operator. Again, we have drones that can go up and down the East Coast, no problem. So we really want to bring beyond line of sight technology to drones. We currently do that. We use satellite communications. We have two examples of those aircrafts on the left-hand side, the Global Hawk and the Icana, the MQ-9 Predator. These are large military-based platforms. And what they do is they have an operator in a fixed location, send the signal up to a satellite. The satellite has global coverage of the Earth, so we can operate our aircraft anywhere we want. Again, these systems are pretty specialized. They're usually very large, produce a lot of power, and essentially the aircraft is built around the comm system. So again, we have a growing community of drones that are going to smaller, higher performance aircraft. We see a couple examples here in the center, like the Viking, the Tiger Shark, the HQ-90s. These aircrafts have very long duration endurance. They can go well outside of line of sight coverage. However, they're smaller and their payload capacity is much, much lower than the Global Hawks and the Icanas of the world. So what our project aims to do is we want to take that antenna technology for beyond line of sight communications and shrink it down in form factors that are applicable to these smaller class UAS and give these vehicles the opportunity to go well beyond line of sight coverage and do coastal monitoring or disaster relief and really open up their mission space by giving them the beyond line of sight technology. So we want to take antennas, we want to make them conformal, we want to make them low mass, we want to put them on all sorts of drones and fly them all over the world. Unfortunately, we're going to have a big issue in doing that. The ITU, or the International Telecommunications Union, identified a interference problem with this situation. So basically, I got in an aircraft trying to point a beam at an antenna out in space. So it's very far, I got to put a lot of energy up. I'm going to try to direct most of my beam up at a satellite. However, energy is going to spill down on the Earth. This happens in what we call side lobes. It's kind of an inevitable fact of physics. And what the ITU did is they studied how much interference we would be causing on the ground if we had widespread drones talking to satellites. Unfortunately for us, the allocation for drones to talk to satellites, we are a secondary user, and the rules are you cannot interfere with primary users. Primary users being very highly sensitive ground-based systems for fixed satellite services. So the ITU said we have to impose a mask to spatially separate drones from these fixed point services on the ground. Do no harm to the people that already exist, basically. So the plot here on the right, we show a proposed ITU mask in black. Basically what happens is we're allowed to put our energy, a lot of energy in one area, and then as we go off angle off that main beam, we have to limit the amount of energy that spills over. So anytime we go over that black line, we're going to fail the mask. The red line is a standard SATCOM antenna, one that we would use on an aircraft like Icana. It's simulated based on a Bessel function. As you can see in situations off the horizon, that red line goes well above the mask. They're about 90 degrees off azimuth. So current technology is not going to meet the ITU mask. So what our project did is we did some analysis on what if we used a phased array to shape a beam. Phased array is a collection of little antennas that we can individually control to basically beam steer or synthesize an antenna pattern. We did some simulations and we came up with an antenna pattern in green. You can see we don't totally meet the ITU mask, but we do a really good job, especially in that area that the ITU is very interested in, that 90 degrees right around the horizon. We are able to dig out a lot of the energy, and we can do a lot of interference mitigation with this technology. So I already predisposed the situation or the solution here for you. We're looking at phased arrays. We're looking at conformal antennas, and we want them to be lightweight. If we look at the aircraft here on the left, the Icana, we got the hood open, so we can see that SATCOM antenna. It's a large volume. It's a mechanically steered dish, and it's got a fixed radiation problem. So there's a lot of problems with this platform. The reason it's being in use today is it's the military and they're special, but if we want this to become widespread for smaller drones, we have to change the way we do SATCOM links. I'm here to tell you phased arrays are basically the answer. Phased arrays are not a new technology. They've been around for decades. The radar guys love them. They give us a lot of power, very high performance. However, it's very, very complicated. This array that you're seeing in the center here was built by Boeing in and around 2000. Something like this is costing us millions of dollars, multiple years of NRE. We got very complex circuits, producing a lot of heat, so we got a lot of metal to pull that heat out. It's just a very bulky solution. It was close, but it was bulky, and it was just not cost effective to start widespread deployment on small aircrafts. Fast forward from 2000 to 2017, when we got in the game, and what happened in 2015, 16, 17 is the 5G market put tons of investment into RF ICs on silicon platforms. What this did is it took these complex circuits that Boeing was doing custom designs for and integrating them down into very small integrated circuits on silicon. So instead of taking Boeing 2 years and a lot of man hours to produce an array, we can buy components off the shelf, and that multi-million-dollar array is costing us tens of thousands of dollars and a much smaller team to develop. So this is actually our flight array that we flew at the end of our project, and we'll get into the design here in just a second. But remember that second word. So we want to be conformal, so we can conform to maybe a fuselage or a wing, but we need to be lightweight. One of the big sells for our project was we have the material science people at Glenn working on aerogels. Aerogel is a very novel technology. It's 95% air. It has very low dielectric constant, very well-controlled pore structure, and very low loss tangent. So us antenna designers really love the material in electrical sense, and the aircraft community likes it because it weighs essentially nothing. It's a piece of almost looks like foam, but don't call it foam because the aerogel people don't like that. It's as light as air, and it has, at the time, it had the great electromagnetic properties we wanted, but it was very brittle in 2015. We did a study in an aero seedling project where we proved that it was feasible to make antennas out of it. However, if you try to bend it, it's going to break. So we're not going to be able to wrap this material around a wing and get some drag savings. So in the last few years, Marianne Meador and her team at Glenn changed the backbone structure of the aerogels, and they were able to make a flexible variant. This allows us to hit very, very tight radius of curvature, and then we still get those electromagnetic properties that us antenna designers love. So we're looking to make a phased array that took Boeing multiple years, multiple million dollars to do. We want to make it conformal, lightweight, and we want to fly it in 2 years. When you say it all out loud, it sounds a little crazy, and it was, but we had all 4 centers to do it. We did the material science at Glenn, we did the antenna design at Glenn, and then our colleagues over at Langley Research Center investigated the mechanical and electromagnetic performance on body with their simulations. Because we wanted to fly, our colleagues here at Ames did the flight planning, basically how can we take an aircraft and make an antenna range in flight. And then our colleagues over at Armstrong, they provided the aircraft itself, did the integration and the flight operations. So getting into the antenna design, I don't have time to get into it. I'm an antenna guy, so I could talk for an hour. Marty would not like that, so I'll just try to hit the highlights here. We have a very novel stack-up shown here on the left-hand side. We do a combination of traditional microwave PCB substrates and that aerogel substrate that was formulated by our chemists at Glenn. So the standard PCB, we try to keep it as thin as possible. Again, we want to flex this around a wing or around a fuselage, so we're trying to keep that material very thin, reduce the layer count, reduce the amount of bond cycles, and then put our aerogel in there, and then that offers us the high microwave performance that we need to radiate our beam out in the free space. Because the aerogel has very, very low mass, we're allowed to get most of the thickness of the antenna lives in the aerogel, and there's no mass penalty. Total stack up on our antenna is about a 1/4 inch, just under a 1/4 inch. As you can see, most of that lives in the aerogel, and if we were to take that design, translate it to all conventional materials, typically microwave substrates are ceramic loaded Teflon. That type of a design, we would have about double the mass that we have with the aerogel. A quick highlight on the antenna design itself. A phased array is one of many antennas that work together to make a composite antenna. So not only did we simulate and optimize a single element, but we had to see how he behaved with 63 of his closest buddies as we made a 64 element KU band phased array. With the front end design done, I'll take a quick note on the back end design. The PCB structure here on the left, the centerpiece of that design is that RFIC that I talked about. This particular chip is 2.5 millimeters by 2.5 millimeters, so it's very, very small, and it's a very complex integrated circuit. We're doing amplitude phase control, power amplifier, LNA, all on chip that can sit behind a very small antenna element. Without this technology, we are not able to tightly integrate our design. This really helped reduce the profile of the antenna. So we did the fabrication process at Glenn. Again, we have on the left-hand side, we see the traditional PCB on the bottom, and then the aerogels that were made at Glenn bonded and put together onto a heat sink. Again, we were looking for conformal, so we wrapped that around a heat sink mandrel. This particular antenna was a 16-inch radius curvature. We were really happy with the way it turned out, and then we were able to flush mount it onto a 16-inch radius curvature cylinder to simulate a fake fuselage. Again, we were targeting the Aeronautical aircraft for this, but again, our antenna would be flush mounted to a surface, no aero drag in this situation, which is what we were after. So we got it fabricated, got it flush mounted, really happy with the way things turned out. It's time to test. We'll talk about 2 ranges at Glenn. We have a far field antenna range and a near field antenna range. The far field range gives us single cuts. So that top plot is simulated expected performance of the array. Again, we have the ITU mask shown in black in the top center plot. Anytime we go over that, we got a bad situation. So the red line is if we were to steer a beam with our antenna and not play any tricks, no beam synthesis, just equal weighting on all elements, point the beam and don't worry about the rest. As you can see, we fail the mask. However, in the blue plot, if we were to apply beam synthesis and do complex beam weighting, we're able to carve out the energy and make a null so that we can meet the ITU mask. Again, that top middle plot is simulation, what we should expect. What's really exciting is the top right plot. That's actual data from our far field antenna range. Again, red being steer the beam, no tricks. Blue being steer the beam with beam synthesis. And again, you could see we really did carve out the energy in the null where the ITU identified the main problem. You can see one of the side lobes is creeping up there at the end. We think a simple calibration can take that out as it came with the uniform plot as well as the beam synthesis plot. Again, this is giving us single cuts, so then we would move to the antenna range, the near field antenna range to get a bigger picture of what's happening with the antenna. So we do a planar scan, and the 2-dimensional plot there in the bottom, the nice colorful plot shows us what's actually happening. Again, we have the beam steered up, and then we're carving interference out around the horizon down where the arrow shows we're trying to take away energy. If you were to draw cuts through that, I'm showing some plots over here. But again, the takeaway here is in the lab, we demonstrated a good amount of interference mitigation with our beam synthesis technique. So the next step would be to put it on an aircraft, see how it performs there. Final goes flight testing, which is costly, takes a lot of resources, so we needed to have a good feeling that our antenna was operating on the aircraft before we even get it in the air. 2 ways to do that. You could take the aircraft to a measurement system, or you can make a measurement system take it to the aircraft. We chose the latter, so we developed what we were calling the Pilgrim, the portable laser-guided metrology system. And this allowed us to take a robotic metrology system out to Armstrong, deploy it at their aircraft, and you can see in the video we're scanning a spherical section of the radiation pattern to see how the antenna is performing. This is patent pending stuff, very new technology. What's interesting about it is we have a collaborative robotic arm. So the robot won't hurt humans. It's not like an industrial robot where it's going to break your arm or you can't have humans around it. And those are inherently not accurate. However, we use a laser tracker to track the end effector and the AUT, or the antenna under test, and that gives us the precision we need to take good quality measurements. Again, we deployed it at the hangar before our flight tests. That gave us really good confidence that the antenna was operating as we would expect, and then we get to fly it. So you can see the T-34C aircraft. Now, this is not a drone. Obviously, we're targeting drone aircraft, but for the purposes of flight testing, we just needed to get our antenna in the air and measure the pattern in flight. So this was a convenient vehicle that Armstrong provided for us. We installed our antenna on the side of the aircraft, drove it around a base station, flew it around a base station, and mapped out the antenna pattern. We did this with precision GPS, INS, on not only the aircraft, but on our ground station that you see in the bottom picture. That allowed us to timeline 2 vectors and sense the radiation environment to essentially map out the antenna pattern. So here's some results. The top 3 plots are measurements taken in the hangar. Again, we have all the data we need here to get the 2-dimensional cut. There's really no restriction on what we can measure. The flight data on the bottom showing 3 configurations. It looks like an incomplete data set because we didn't have the pilot do barrel rolls. We just had them concentrate on the areas of interest that we wanted to measure. In the first column, you can see that we have the beam pointed down. We show the main beam in the flight test. It agrees well with the hangar data. Same thing with the middle column. We're steering the main beam up, so we're only measuring side lobes, but again, we get great agreement. The final data plot is where we're trying to limit the energy on the ground. So if you really think about this, we're trying to make it so the ground receiver doesn't see anything. Having a little blob of energy that's really undefined was a good thing here. I'm not going to get into quantitatively what this data means, but the takeaway here is we got really good agreement between our ground system with our Pilgrim and our flight testing and the way we operated. So to sum it all up, we're looking for conformal, lightweight antennas for small UAS. To do that, we developed the aerogel substrate, made it flexible, got great microwave performance, really low mass. Then we leveraged our new COTS RFICs, which were basically pre-release. We got the very first run, pre-production run, when we made the antenna back in 2017. We were able to fabricate our antenna with a very small team, low mass, low profile, got it integrated on an aircraft. We were able to demonstrate the interference mitigation in the lab, so hopefully the ITU can feel good about phased arrays solving some of their interference problems. Along the way, we made the Pilgrim and had a great flight campaign. All this happened in about 2.5 years, so really exciting program. And I'll leave it at that and open up for questions.
John, very clever to use up some of his Q&A time, telling us a little bit more than
All right, we have a new member from Boeing Horizon X Venture Capital. So Dominic, would you like to introduce yourself?
Hi, good morning. My name is Dominic. Sorry about that. Good morning. Take 2. I'm Dominic Mycroft. I am with Boeing Horizon X, and I lead the mobility transformation vertical within our corporate venturing arm. And is that good? Okay.
That's good.
Anything else?
All right, so who wants to start the question? Thank you. By the way, CLAS-ACT indeed. So, any questions for Brian?
Well, really good stuff, so very impressive. So outside of what your focus there is, any sort of other applications that you think this might be applicable to, broadly speaking?
So I'm an antenna guy, right? Interested in phased arrays, active antennas, machine learning, autonomous vehicles. That's all the hot topic. So I think we can all agree that without comm, UAM, autonomous vehicles, that can't happen. What's interesting about phased array technologies is it's a flexible thing that gives you knobs to turn. So you want to learn about your system, you need knobs to turn, you need stimulus, you need to generate stimulus. Well, the phased array gives you that in the comm system. So one of the topics at Glenn is we want an autonomous vehicle. Why not have an autonomous comm system? So why can't your comm system takes the burden off your primary avionics? And phased arrays aren't limited to aircrafts. Automotive industry's using them. The radar guys love them. They've been using them for years. Anytime we can make phased arrays better, lighter, it's just good for everybody.
Okay.
Go ahead, Jim.
So I'm trying to understand just a little bit more about the capabilities that this would enable versus something like an existing satellite phone system. So with your phased array, I'm assuming that you're saying that you can now access a wider variety of satellites, existing networks, opposed to, let's say, a phone that's only going to be able to connect with a certain satellite with a certain antenna that's already up there. So is that the plan? Is it basically opens up the communication spectrum to a much wider variety of satellites?
All right, so let's be careful how we use spectrum here. Phased arrays are going to offer us spatial separation between users. In all systems, automotive, aircraft, people, the user base is growing. Interference is becoming a problem. The 5G market saying we can do phased arrays for spatial separation, and they're absolutely right, but you gotta play a lot of tricks to make that happen. If I'm talking over here, I can't let somebody else drown my signal out from over here. So I need to block that out, which is what we demonstrated with the interference mitigation. The phased array gives you the opportunity to do a flexible spatial beam. That's what's novel about the technology. Well, it's not novel to phased arrays, but bringing that technology to smaller platforms is what's novel about what we're doing. So yes, handheld devices are a little bit tricky, but yeah, there's gonna be phased arrays, there's gonna be directional beams on that in the 5G market, and the 5G community is trying to figure that out now. So the aviation community and the 5G community are trying to learn how to do this together. We're leveraging their investment. Those RFICs don't happen without the billions of dollars that 5G puts into it. So we benefit from them, and hopefully they benefit from some of our technologies as well.
Okay, so one question I have is, you talked about work that you did that enabled you to create a curved conformal phased array antenna. And so am I correct to understand that all previous phased array antennas have been planar? Is that basically the case?
No, that's not accurate. So phased arrays are not novel. And conformal phased arrays, you get a textbook, they'll tell you how to do it. What's novel is the way we integrated, doing the tight integration and that aerogel material to really reduce the mass is what makes this technology novel.
Okay, and so one of the ramifications of creating this capability that you have is that on a given size UAV or other aircraft, because you can now create a conformal phased array, you could arguably put a larger phased array antenna on that vehicle than you otherwise would be able to if you were constrained to planar, right?
Absolutely.
And so how does
even if I can stop you,
Yeah.
even planar is a step up from those parabolic reflect antennas
sure.
that have high volume.
Sure. So you talked about reducing interference with other assets that are going to be on that frequency. How do you see that contributing to overall communications resilience in a high-density network where you have a lot of air vehicles? I mean, I can almost make that conceptual leap, but you've been living in it, and so how are you thinking about that?
Yeah, so the UAM idea is this beautiful image of multiple aircrafts flying all over the place, talking everywhere. When you have that many users in a dense space, your comm system you have to play all the tricks. You need time division multiplexing, you need frequency division multiplexing, but I'm gonna go ahead and say that that's not enough. You're gonna need spatial separation as well. And that means you need flexible beam shaping. You have to have a phased array to do that. You really can't do any kind of steering and high performance interference mitigation on traditional antennas. You know, the whips are omni, so they're just spewing their antenna all over the place. And they're dealing with frequency division hopping and time division multiplexing, and that's how they're getting around having multiple systems in the same environment. Once that grows, you're gonna start running out of channels. Again, spatial separation is the next step to increase the user base and make it more reliable.
So Brian, is your secret sauce software or hardware or both?
So, what's interesting about phased arrays and now, the hardware is what makes it good now. That's, the time is now with these RFICs. So the hardware development is gonna shoot through the roof, and the software development is going to, it's gonna just kind of tag along. We actually flew a Jetson as our payload, so we would be able to do the very math-intensive computations if we needed it to. But for a lot of beam steering, you could do this stuff with a microcontroller. So it depends how intricate you want to get into the control system, but it could be very, very complicated. You could your antenna pattern could be a machine learning algorithm where it senses and it adapts and it says, oh, I have a user over here. Now we're talking about some kind of a GPU and some really, really complicated software, or it could just be point a beam and point a null, and that can be done with a microcontroller.
I would love to learn more about how you're thinking about commercialization, you know, as you look at the competitive landscape out there. You mentioned Boeing, you know, we've been working on this, and I'm sure all of the other aerospace giants and startups have been working at. What are your thoughts on next steps in terms of how are you going to commercialize it?
That's a great question. So everybody's been on an aircraft where you got the go-go service. They're talking to a satellite. They have a huge antenna on the top of that aircraft. And that's fine because they have the power and that's the state of practice. Our market, being small aircrafts that can't afford to put that giant aperture, is going to drive us to make technology advances like the aerogel, and that's going to trickle up to general aviation. The DoD loves this for all sorts of platforms. As far as commercialization, our aerogel materials are licensed by Aerogel Technologies LLC, so we're getting that out into industry. I think we have a new technology report on the phased array itself. How that infuses into general aviation, I haven't really thought of. I know we have to advance this for UAM, but the DoD is the one that is really the most interested in grabbing it. Again, the Boeings of the world are doing it for the DoD already, and we're kind of along to help.
Did you have a question, Peter?
No, I'm okay for now, yeah.
Oh, yeah, I.O.
We got about 2 more.
Okay, do you want to answer any one of those? They're equally rated with number one,
I
so,
think I just covered that, right?
yeah.
RFIC.
The bottom one is about flexing of the structure, aircraft structure with the conformal.
Yes, it absolutely will.
I've seen that, by the way, yeah, flexing it, so go ahead.
There is research out there, when your surface changes, your antenna spacing changes, your element morphs a little bit, so that impacts the performance of the antenna. And a lot of times you can't get around that. If we were to take a small drone and paint a phased array on the wing is going to flex and it's gonna change our pattern. What's interesting as a research topic for a guy like me is how can we adapt? A phased array gives us the opportunity to compensate that, right? The wing will flex, we can compensate as long as we know how to compensate for it. So if we can sense the flexure or sense what's changing in the environment, we can reweight the array and re-optimize the beam. I think that's a good research topic. That's great follow-on work. I know Boeing and other research entities are already looking at that with just wing flexure studies and all sorts of measurement systems for that.
And when would you say you're done with this? What's your, sort of, you accomplish and it's finished, or is it one of those things you keep, reduce drag, keep on trying?
I think this could be a growing technology. James Downey and myself are trying to push phased array technologies at Glenn and and morph it into a bigger program. It obviously doesn't stop with the hardware. I think the next step here is on-body reoptimization. We made the Pilgrim. That gives us the opportunity to measure on-body, recalibrate, reoptimize. If we can figure out that calibration of the array, then we can start doing interesting things like machine learning algorithms on self-optimization and self-health monitoring for the antenna. And I think that really that's kind of far out technology. If we get to a point where the antenna can be put on one wing, sense its environment, reoptimize itself, and then that same antenna goes to the next vehicle, gets put on the fuselage, senses its environment, reoptimizes itself. That's where we want to get. We're not super close to that, but I think this study showed that the hardware is ready, and we're ready for the optimization routines.
All right, thank you.
Perfect timing.
All right, perfect.
Harry, do you want to squeeze one in real quick? We'll repeat the question up here for you.
Coordinated any with NextFlex, the Manufacturing Institute, and what they're doing on antennas?
Next flex.
The question was if we've coordinated with NextFlex. I'm not familiar with them.
So we formed the DoD Manufacturing Institutes, and they came out with a call on flexible electronics 2 or 3 years ago, and they've made pretty good progress on conformal antennas. I just wondered if you worked with them. You might want to look them up.
Sure, thank you.
I think we did have some discussions.
Was that from the antenna working group, maybe?
Yeah.
Yeah.
Okay, so let me ask the question to VCs, how are we doing in coming up with the names? Are we better than the outside world, are we same, or kind of behind on
Coming up with what?
the acronyms, CLAS-ACT and attractor and all those things? Fit to fly.
I think you're doing fine.
Far superior.
That was a trick question.